We're going to look at the problem of try to find all prime numbers up to a given integer n. For example, try to find all prime numbers less than 100. Alright? So a naive way of doing this problem is just try each number and check if it's a prime number or not, right? So for example, how do you check if x is a prime number? You're going to check if number 2, 3 up to x minus 1 is a factor of x. If it is, then x is a composite number. If not, then x would only have a factor of 1 and itself. By definition, it's going to be prime number. Of course, one optimization you may be able to do is to think about if a number x is a prime number, then you can check up to square root of x, right? So you don't have to check, all numbers up to x minus 1, right? And this is because if x has a factor, it must have factor, no greater than square root of x, right? Because the remaining number would be x divided by that factor, right? So if you have two number multiplication equal to x, one of them must be, no greater than square root of x. Okay, so if you do that, the algorithm would be, in order to find all prime numbers up to n, what you do is you check each number x, right, that is less or equal to n, and to check if x is a prime number. How do you check the x is a prime number or not? You do another for loop, right? To see, you check each integer that is no greater than the square root of x. Here, square root of x could be a non-integer, right? For example, square root of 7. So here, what you do is this symbol is the ceiling of the number, all right? So if the square root of x is 6.5, then the ceiling would be 7, all right? So that's algorithm. But today we're going to introduce what is called the Sieve of Eratosthenes. This is a Greek mathematician. He figured this out about more than 2,000 years ago. So this is how the algorithm works. You list out all the numbers. Notice that we skip number 1, because by definition number 1 is neither a prime number nor a composite number. Number 1 is special, right? So the first number you see here is 2, so we call it prime number, all right? And then what you do is you're going to sieve out all the multiple of 2's. You keep 2 as prime number. You get rid of all the multiple of 2, like 4, 6, 8. Let's do that. All right. Those even numbers are gone. Number 2 is a prime number. And then you continue the process. The next number you see is going to be 3. All right. So number 3. And then you take it as prime number. And then you're going to remove all multiple of 3's for the remaining numbers. All right. So you notice that number 6 was already removed. So don't care about that. The next number you're going to remove is number 9 and number 15, right? And number 21, and so on and so forth. So in these steps, we're going to remove all multiple of 3's. Now the next number is 5. It is a prime number. Why? Because there's no factor smaller than it. Because if there is a factor, then that number must be removed by that factor, right? So 5 is a prime number. You take it, and then you're going to remove multiple of 5's. All right, let's do that. And all the multiple of 5's are gone. And then next one you see is 7. So 7 is a prime. You take it as a prime, and then remove multiple of 7. All right, let's do that. Now notice that we're pretty much done. Why? Because we're looking for number up to 100, and the square root of 100 is 10. So there's no need to check factor greater than 10 for all the remaining numbers. Everything remaining must be prime numbers. So if we do next iteration, we're gonna know that all the remaining numbers are prime numbers. So we notice that there are about 25 prime numbers that is less than 100. Alright, so here we can run the algorithm. Let's say if we want to check 400, right? So here, let me make it smaller so that you can see the button here. Alright, let's just illustrate the process. Again, the first time you're going to see number 2 is a prime number. You get rid of the multiple of 2's. Next number is number 3. You get rid of number 3's, multiple of number 3's. And next is 5. You get rid of multiple of 5. Get rid of multiple of 7. Get rid of multiple of 11. And 13. 17. And 19. Now you should be done, because again, 400 square root of 2 is 20. There's no point of looking for a factor greater than 20 in this case. All the number that is left must be prime numbers. So we can see that we're done. All the numbers marked here are prime numbers. There are 78 of them. Alright? So that's kind of the illustration of how algorithm works. Hope you enjoyed the video, and please subscribe or leave comments if you have any suggestions on the subjects or on this topic itself. Thank you.